Hello everyone and welcome to the NPTEL course on pharmacognosy and phytochemistry. In this week, we are dealing with a set of compounds called as glycosides. In this session, we will learn more about terpenoidal glycosides, especially the diterpene and the triterpene one. So if you remember in our previous chapter on lipids where we did volatile oils, we discussed few set of compounds called as terpenes. Those were the ones which were derived from the isoprenoidal pathway. Now this terpenes, depending upon the number of isoprene units that have been attached to it, can be categorized as monoterpenes, diterpenes and triterpenes. So monoterpenes are the ones we studied in our volatile oils, and comparatively as the molecular weight increases, we come across diterpenes and triterpenes. Diterpenes are the compounds containing 20 carbons, whereas triterpenes are the compounds containing 30 carbons. So let's understand diterpenes and triterpenoidal compounds as well as their glycosidal derivatives. So we'll discuss triterpenes first. Triterpenes are the compounds which are derived from isoprene units, and if you go to see, they are C30 compounds. So in all you will come across 6 isoprene units which have been joined together. So if you try to visualize it, you can visualize isoprene units as 1, 2, 3, 4, 5 and just cut it from here. You can see the second isoprene unit till here, the third isoprene unit till here. Now what happens here is there is something called as tail to tail condensation. So instead of forming a head to tail condensation, this tail to tail condensation causes almost an inverse symmetry. So you can just imagine, starting from here you have your next terpene, that is your isoprene unit, the next isoprene unit and the last isoprene unit. So you have about 1, 2, 3, 4, 5, 6. 6 isoprene units which are joined to each other. Now each of this isoprene unit contains 5 carbons. So 5, 6 are naturally we have C30 compounds which are combining to form triterpenoidal compounds. So if you go to see triterpenoidal compounds, depending upon how they cyclize or how they condense, the biggest linear chain triterpenoidal compound which you see occurring in nature, the aliphatic one, is your squalene. Now this squalene, depending upon the enzymes it encounters, it might fold in a way that you will get a 4-ring structure, and you can call this A ring, B ring, C ring, D ring, wherein a D ring has 5 members. This essentially gives rise to set of molecules which are called as steroidal triterpenoids. Now in this case what happens is, if I just join it here and I'll again get A, B, C, D, but this time D has 6 carbons and an additional ring which is an E ring. So in this case your squalene molecule will give rise to compounds which are called as pentacyclic triterpenoids. So your steroidal triterpenoids as well as pentacyclic triterpenoids have their genesis from squalene and are made up of 6 isoprene units. Now one good example of a triterpenoidal compound which is having a steroidal nucleus are damarine type of triterpenoids which we see occur in ginseng, and another set of triterpenoidal compounds where you see a 5 ring system, that is your pentacyclic triterpenoids. Now there are numerous triterpenoids and there are more than about 100 categories structurally, but if we have to broadly classify them, the most common types are your alpha amyrin, beta amyrin and lupiol. So what happens here is, as you can see, your alpha amyrin beta amirin and your lupiol differ somewhere in their E ring. Okay. If you go by numbering, we can have the same numbering 3, 4, 5, 6, 7, 8, 9, 10. The one which we studied in steroids. So again this is going to give you 11, 12, 13, 14, 15, 16, 17, 18. So here you are going to have your 18 and then onwards you will see your 19, 20, 21, 22. Okay. Now this substitutions, the methyl substitutions, especially on A ring, you will see 23, 24, then you have your 25, then you have your 26, then you have your 27, then you have your 28, this methyl, and this, the last two methyls of the E group get the number 29 and 30. So you can see all in all we have 30 carbons accounted for. Now when the terminal methyls, the last methyl of E ring, one of the methyl occurs in 19 and the second methyl occurs on 20th position, we call this set of compounds as alpha amirin. But when your 29 and 30, both of them occur simultaneously on a single carbon, and that is your carbon number 20, we call those compounds as beta amirin. Now a little change to this is, rather than having a 6-membered ring, if we have a 5-membered ring, what happens here is, you can see here 19, but the 20th carbon, imagine I cutting it from here. So the 20th carbon is kind of protruded out. So this is your 19, this is your 20, and again this imagine to be your 21. So what happens here is, again your 29 and 30 are located here. In this case, when you have a 5-member, your 20th carbon is out with the substitutions, that is the methyl substitutions on 29 and 30. Such compounds are called as lupiol derivatives. Now you might have other derivatives also, depending upon how the rings cyclize, where the rings open, and also depending upon the nature of substitution, especially with regards to oxygen. Many of the triterpenoidal class are derived from it. So we start with the first example of a triterpenoidal pentacyclic glycoside compound, and that is your licorice. Now licorice or licorice, there are two spellings to it. The LICORICE is an American one, whereas LIQUORICE is a British one. So both of the spellings are right. In Indian system we call it as Jeshtimad or Yashtimadu. Now this contains especially the underground parts. Underground parts includes the roots as well as what you call it as the runners or the stolons. Both of them are cut, collected. So you might have the entire one or you might have it cut. Now in some cases the outer peel, we call it as cork, has been removed due to processing. In some cases it is there. So you might have it peeled, you might have it unpeeled, you might have fresh, you might have dried, you might have cut, you might have uncut. Now there are numerous species of licorice which are there. The most common ones which are there in market are your Glycyrrhiza glabra, Glycyrrhiza inflata or Glycyrrhiza urulens. So these are the common ones and belong to the family Fabaceae. Now most commonly licorice is cultivated and occurs in Russia, Iran. If you go to Middle Eastern countries, you will get a lot of this licorice candies. So it also cultivated in Spain, Afghanistan and also in India. Now the main ones, the main licorice of commerce are the Spanish and the Russian ones. So if you go to see Spanish, they are little shorter or smaller with a length of about 14 to 20 centimeter and a diameter of about just like 5 millimeters or 20 millimeters, like your 2 centimeters max, with a reddish brown cork. Whereas if you see Russian variety, it is much thicker. The diameter may be as big as 5 centimeter as opposed to 2 centimeter, and the length is about 30 centimeter or so, about a foot long, and has a slightly purplish color cork. But if you break this, you might see internally a slightish yellow color pigment is present, and that's attributed to the compounds present in it. So licorice contains triterpenoidal glycosides, especially pentacyclic triterpenoidal glycosides belonging to the uracil category. Here you have what is called as a pentacyclic triterpenoidal compound called as glycyrrhizinic acid. Now in plant it occurs as salt form. So you might have a sodium or potassium salt out here, and the sodium potassium salt of glycyrrhizinic acid is called as glycyrrhizin. So the most common saponin, what we can say, is glycyrrhizin. Now why am I calling it as saponin? So saponins are the ones which show surfactant like properties. So if you observe this molecule carefully, you see a little polar entity out here made up of your sugars, that is a disaccharide, and if you see here, here is a more non-polar entity. So when you have a non-polar entity with a polar head, they act like surfactants, and if you put them in water, they tend to produce foam. So glycyrrhizin or glycyrrhizinic acid is basically saponin in nature and responsible for the foam produced when licorice is soaked in water. Now if you cut out the sugars, you get the glycone part, and the glycone part is named as glyceritic acid. So glyceritic acid is a glycone part of glycyrrhizinic acid. Now apart from that, we were just discussing licorice. When you cut it open, you see a slight yellow coloration, and that yellow coloration is attributed to flavonoids which are little yellow in color, such as your licoritin, isolicoritin, which is kind of a chalcone, isoflavones, glabrin, glabridin, licochalcones A2E. You also have compounds such as glycomarins and some coumarins present. So these are the ones which make up the chief composition of licorice. Now you can check licorice by doing numerous chemical tests. The first one is you can check if it contains the flavone derivatives, such as especially the chalcone derivatives. Now when you take this plant or a section of it and then add about 80% sulfuric acid, you will see that initially this part of plant which is exposed to a 80% sulfuric acid produces a orange yellow coloration, and this happens because your flavones get converted into chalcones therein, and that gives you a nice yellow orange coloration. The second one is because it contains flavonoids. More than 20-30 flavonoids have been reported in this plants, and some papers cite more than 50 flavonoid derivatives being reported. So if you take this, and this is what the Shinoda test is all about. So if you take the alcoholic extract of this plant, that is you take the plant powder and boil it in alcohol, and to that if you add your magnesium turnings in presence of concentrated hydrochloric acid, reduction of flavonoids take place and they get converted into anthocyanins. These anthocyanins are colored compounds and gives you color ranging from orange to pink depending upon the nature of flavonoids. So this is your Shinoda test, and as you can see here, this is the extract. Because of the yellow flavonoids present, it's already showing yellow, but when you treat it with magnesium turnings and concentrated hydrochloric acid, you will see that the color intensifies, changes to a little orange pink hue, and that indicates some anthocyanins have been formed during the process, and that's a Shinoda positive. Whereas if you go to see the next test tube, that is what we call it as the saponin test. We discussed earlier your glycyrrhizin is a saponin. So if you just soak your licorice or boil your licorice and then gently shake it, you will see that it produces a foam. Now this foam, despite keeping it for a period of 5 minutes, also doesn't subside, and that's what we call it as stable foam, and this foam is stabilized by surfactants. What are surfactants here? The surfactants here are your glycyrrhizin. Okay, so because of the glycyrrhizin you get a saponin test or foam test positive. Another test what you can do for saponins is a hemolysis test. So if you take blood sample, this is not possible much to do in a chemical lab, but if you have access to blood samples, if you take blood samples and if you drop saponin extracts or extracts containing saponin there, that produces hemolysis, that is your RBCs split open, and that hemolysis test is also a test for saponins. Applications, licorice is being used, or Jeshtimas has been used in Ayurveda. It is known as a rasayanam or a rejuvenator. Licorice is used in candies for the reason the glycyrrhizin it has, the saponin it has a very sweet taste or a sweet flavor, almost up to 100 to 150 times as that of your sugar, that is your sucrose. So you get a derivative in market called as ammonium glycyrrhizinate, which is nothing but an ammonium salt of glycyrrhizin, and that is also approved as a sweetener. It has anti-inflammatory activities, it has demulcent activities, and as a result you will see that in Ayurveda, even in your cough syrups, small amount of Jeshtimad or licorice has been added. So it acts as a mild expectorant, as an anti-inflammatory agent. It helps you in dealing with the peptic ulcers. Now one more important thing about the licorice is it has what is called as mineralocorticoid or adenocorticoidal activity. Now what is this is, near your kidneys there are adrenal glands which secrete something called as cortisol. So in patients suffering from Addison's disease, those are not produced, and as a result especially the sodium and the water retention doesn't occur properly. Now in such cases, when you consume licorice beyond a particular dose, they act as your mineralocorticoids. They help you in water and sodium retention, and as a result provide relief to the patients. It is also reported to have antibacterial effect. It helps in dealing with chronic inflammation, and this property is attributed to the flavonoid derivatives, especially for arthritis, inflammation of skin, rheumatoid arthritis. Now one more interesting finding is in cosmetics nowadays, a derivative, that is a flavonoid, which is present in licorice, glabridin, is studied to inhibit tyrosinase, the enzyme which is involved in melanin synthesis, and since it stops the melanin synthesis, there is a whitening effect observed in skin. So glabridin is used in skin brightening creams. Now licorice, because of its adrenocortical activities, need to be taken with caution. It is known to alleviate. So if you consume licorice for a longer duration of time, it can lead to what is called as elevated blood pressure, definitely, and hypokalemia. So these two things need to be done with cautious if you're consuming licorice on long term daily basis. So we move on to the next drug, and the next drug is a part of, if you've seen the prescription or if you've seen the label of your vitamin supplement Revital or many other immune modulators, you might come across this drug called as ginseng. So we'll study ginseng, what it is. So ginseng is actually a root of a plant belonging to the genus Panax. Now this is a huge genus, but many subspecies of it show a very good immunomodulatory effect or adaptogenic effect, and these are your Panax ginseng, which is also referred to as your Korean ginseng, Panax noto ginseng, which is Chinese or South China ginseng, Panax quinquefolius, or which is also referred to as American ginseng. They belong to family Araliaceae, and if you see the roots, they resemble human like figure, and that's why they said that it's very good for body. If you're feeling tired, it kind of helps you adapt with the stress, so it's a stress relieving agent as well. So what does this ginseng, or what are the types of ginseng? So if you go to see in market, there are numerous types of ginseng available. The one, if you go in China, you get what is called as a fresh ginseng. So fresh ginseng is generally harvested from plants which are less than 4 years of age and eaten as fresh, just cut and eaten up. So that's your white one. Now this may be kind of peeled, dried and eaten, and what you get is a white ginseng. But in some cases it is heated or steamed. Now during the process of heating or steaming, some extraneous compounds undergo deterioration, some sugars undergo caramelization, and you get a typically reddish color outer coating, and that is what is sold in market as a red ginseng. And sometimes it is also baked or puffed, so you also get in market what is called as puff red ginseng, which you can just consume it like a snack. Now there's also something called as sun ginseng, which is a steamed white ginseng, but much higher temperatures, pressure combinations are used in processing. The last one is sought out Korean black ginseng. Now what is done is, this is the same red ginseng, but it has been steamed, cooled multiple times. So some of them say about 9 times it is steamed, cooled, dried, and this process, instead of red, it now achieves a extraneous black coloration, and that is sold in market as black ginseng. So if you see chemical composition, the chemical composition of ginseng is more of a Damarine type of compounds, what we studied, that is your steroidal triterpenoids. Now in steroidal triterpenoids, this is your 10 and this is your 19. So if you see with respect to 20, this 20 you get 20R and 20S isomers. So it is said that your 20R isomers of ginseng, called as ginsengosides, especially the glycosides of it, are much more potent. Now this glycone part is called as protopanaxodiol or protopanaxotriol. Now protopanaxodiol will have especially a diol at C3 and or at C20, whereas if you see your protopanaxotriol, it will have an additional hydroxy here. This is your C6 position. So you will have C3, you will definitely have your C20, but in addition there is also be a hydroxy at your C6 position in addition to your protopanaxodiol. So you have protopanaxodiol, protopanaxotiol, and to all these hydroxides you will see your sugars being attached. Now these sugars, when they are being attached, they will make the molecule more and more polar. So there's an interesting findings. Now in naming the ginsenosides, what they did is, if you remember in your chromatography, there is a technique called as TLC. So in TLC you have something called a stationary phase and a mobile phase. So assuming your normal TLC, your stationary phase is generally polar and your mobile phase is generally non-polar. So what happens here is, when I spot my compounds in TLC, because my mobile phase is non-polar, all my polar compounds stay back and all my non-polar compounds run with the mobile phase. So interestingly, because ginsenosides were many, the nomenclature came wherein R was your retention factor. So Ra was the most polar one. We even have R0 to be frank, and then you go on like Rb, Rc, Rd, Re and so on till Rg, and then depending upon the slight fractions you had Ra1, 2, Ra3, Rg1 and 2. So Ra1 is the most polar, so having up to 5 sugars being attached to it, whereas as you go up more and more non-polar, the sugars decreases. So when you come up to Rg, you might just be left with 1 sugar being attached to it. Apart from that, you have your ginotonins, you have your polysaccharides called as panaxans. Now where do you use it? Like I said, ginseng is used as a tonic and stimulant. It is adaptogen, it will help you deal with stress, noxious effect of many nature, physical, chemical, biological, and it is capable of improving your memory and intellectual skills. It is also given an alcohol intoxication therapy because it's good for liver. It's said to be liver protective. And like I said, the R derivatives are more potent. So 20 R Panax ginsenosides have been used for or have been studied extensively for cancer and therapies, chemo prevention. All in all, ginseng is an excellent immunomodulatory, neuroprotective, cardioprotective and anti-inflammatory. Going on to the next set of compounds, which are diterpenes. This contains C20, that means it contains 5-4-za. So here you have your 4 isoprene units. So this 4 isoprene units will join head to tail to form what are called as diterpenes. They might again, depending upon their enzyme, cyclize and give rise to various compounds. The good example of diterpene glycoside is a sugar derivative called as, or a sugar substitute called as stevia. Now stevia is obtained from leaves of a plant which belongs to the Asteraceae family, and that's your Stevia rubaudiana. Now there are numerous species in that, but Stevia rubaudiana is thought to be the most sweetest variety in that. So stevia cultivation happens in South America, Paraguay, Brazil, Japan. Also it started in India with, we have our own stevioside producing factories now in India. Now the sweetness of stevia is due to different stevia glycosides. The glycone, that is this inner part, is referred to as steviol. And to this steviol, depending upon the number and depending upon the nature of sugars attached, you have your stevioside, which you can clearly see has 3 sugars. You can see your rubaudioside. The steviol is same, the sugars change, which has 4 sugars, and numerous stevioside derivatives have still been discovered of the plant. Apart from that, other derivatives include your stevia monoside, rubusoside, dulcososide and steviol bioside. So these are also compounds which kind of are diterpenoids and contribute to the sweetness of the plant, but the majority in terms of their content and in terms of the sweetness are your stevioside and your rubaudiosides. Now applications of stevioside is, if you see countries like Japan, they are trying to replace their sugar completely by steviosides as a non-calorific alternative. So it is safe to give for people suffering from diabetes, high blood pressure and obesity, where you really want to curtail the saccharide or the sugar intake. In terms of their sweetness, they can almost replace, if you see stevioside, it can replace like almost 150 to 300 times sugar. Or if you see rubaudiosides, they are still more sweeter and then can replace 250 to 400 times sugar. Now from this set of molecules, if you specifically pick up rubaudioside M, that has been commercialized by companies such as Pure Circle and Coca-Cola. Now rubaudioside, when studied in certain animal models, have also reported to help increase the insulin production. So that's also a little advantage of stevia. So with this, we end our today's session on terpenoidal, especially the triterpenoidal and diterpenoidal glycosides. Here are few references for your reading. And thank you everyone for your patient listening.